For our first talk this afternoon, we're very pleased to welcome Mona Merling, who will be speaking on toward the equivariant stable parametrized h-cobordism.
Thank you, Tyler, and thank you to all the organizers and all the speakers so far and forward. I think it will be very hard to live up to the great talks that we have seen so far. So I'm going to talk about a joint project with Kerry Malkiewich. So let me give some motivation and background from, as you can see, I almost forgot to put the crucial word, which is equivariant. So let's start with the non-equivariant story and even just a classical story on the h-cobordism theorem. So let me do a quick review of that. So if you have a compact, smooth, n-dimensional manifold, did I do something funny?
He's excited.
What's that? Oh, okay. All right, so let's give the definition. An h-cobordism, or maybe let me say it like this: WMN is an h-cobordism if W is a compact n+1 dimensional manifold. So n is also n-dimensional, such that, okay, so the condition for being a cobordism is the boundary of W is M disjoint union n. So this is what it means to be a cobordism. And then what makes it an h-cobordism is we require the inclusions of M and N into W to be homotopy equivalences. Okay, so some examples and non-examples. The usual example of a cobordism, which is the pair of pans. Maybe we can put some holes in there. So of course this is a cobordism, but it's not an h-cobordism. Right, so clearly a circle is not homotopy equivalent to two circles. So the only example of an h-cobordism that I can draw for you is the trivial one. And maybe you can imagine some twisted version of it. So if you're given some other cobordism, the big question is it diffeomorphic? So is W diffeomorphic to the trivial one? Right, so you can now try to imagine one that's not, and you're probably not going to be able to imagine one that's not. But they exist. So they exist, but this theorem is going to be for high dimensions, so you can probably not quite imagine it. So the h-cobordism and s-cobordism are theorems of Smale and Barden, Maser, and Stallings. So I'll combine it into one statement that says that so now the condition is the dimension of M has to be bigger than or greater to 5, and it says that the diffeomorphism classes of h-cobordisms on M is in one-to-one correspondence with this algebraic object, so it's a group, the Whitehead group of M, which is by definition a quotient of a K-theory group, just K1 of the group ring of pi 1 of M, mod plus minus G in pi 1 of M. And also recall, so how is K1 defined? K1 of a ring is just the Abelianization of the general linear group. So it's really defined in terms of linear algebra. So this has a very concrete definition. However, these Whitehead groups are quite hard to compute. So despite a very easy to understand definition, if you try to compute any, it's going to be very hard unless we take, so let's take the really easy case where the fundamental group is trivial. Okay, so then k1 of z, so then we get k1 of z mod plus minus 1, and using some linear algebra you can see that this abelianization for z is equal to, it's just going to be the units of z, so plus minus 1. So this is trivial, so this implies that, so if for m simply connected, every h-cobordism is trivial. So this was Smail's result, and then it was expanded further to this more general statement, which is called the h-cobordism theorem. Okay, so in particular we have this, and in general, I'll refer to this later. The way it goes is, so you can define an element in the Whitehead group. So in general, W is trivial if and only if, so there's an element associated to this homotopy equivalence, this inclusion. This is an element of the Whitehead group, and this is 0 if and only if your cobordism is trivial. Okay, so now you can make a whole space of h-cobordisms. And so I'll just tell you what the points are. So we can view them as codimension 0 embeddings, submanifolds of m times I, which are h-cobordisms on M. You can give it a topology, you can build it in a simplicial way, and then there's also a stable version. I'll call it H infinity, which is by definition the co-limit of these unstable ones where we cross with intervals. And then there is a stability theorem of Igusa that says that the connectivity of this map is roughly n over 3, where so n was the dimension of our manifold. So in high enough dimensions, the homotopy groups of these two become the same. So let me just make some remarks. So pi naught, so we can view the h-cobordism theorem not as a pi naught statement. So we can say pi naught of this stable h-cobordism space is the Whitehead group. Right, so maybe I should also say this, what the points are, but also you have a path if you have a diffeomorphism. So this is so our pi naught is going to be by definition the diffeomorphous classes of h-cobordisms. And this is actually not just a space. The other remark, there exists a spectrum HM, maybe let me make it bold, with whose underlying infinite loop space is this stable h-cobordism space. Okay, so why do we care about the space? So the reason why people care about it is that if you want to compute the homotopy groups of B-diff, this fits in a fiber sequence where diff tilde of M, this is the group of block diffeomorphisms, so something whose homotopy groups are accessible via surgery, and then the fiber is this quotient, and the point is that these homotopy groups are computed by a spectral sequence with input the homotopy groups of these h-cobordism spaces. Okay, and this is work of Hatcher, Weiss, and Williams. Okay, so we'd want to understand the homotopy groups of this stable h-cobordism space, and then the groundbreaking theorem of Waldhausen was that you can reinterpret this in terms of K-theory. So Waldhausen, so he defined A theory of X as, so this is the K-theory of the space X. For a long time, so it's defined as the K-theory of the Waldhausen category Rx of retractive spaces over X. So for a long time, I was trying to figure out what A stood for, and nobody seems to know, but I realized that, of course, you don't want to call it K-theory because there's topological K-theory of spaces, and you don't want to confuse those, so it probably just stands for algebraic K-theory of the space X. But, okay, if anybody knows the story, you can confirm it. Okay, so this is the algebraic. So that's my conjecture. But so this is the algebraic K-theory of the space X, and the point, so the reason why he invented this and all this machinery was to prove the following theorem, which in the end was proved with Yaren and Rognes. That, so now M I will take to be a compact smooth manifold, that the A theory of M splits as the suspension spectrum of M times some other factor such that loops on this factor is this h-cobordism spectrum. Okay, so great, we fill the boards. Okay, so this is the classical story. And now what is the goal of our project? So this is the classical stable parametrized h-cobordism theorem.
So are those spaces or spectra? You're sort of looping something and it looks like that's a space, but then you have suspension.
So they are spectra, or you can also write this on the infinite loop space level. So before I define this as a, so I made a remark that that's actually a spectrum, but I could have written this on the, so it's not just a decomposition of spaces, but it's actually of infinite loop spaces. Right, so then I could have written like Qx and taken the A theory space here and just consider spaces, but they're all infinite loop spaces. Okay, so the goal of our project is, okay, so there's a bunch of things that we need to define in the statement. So we want to define AG and WG such that, and prove a decomposition analogous to the non-equivariant one. Where, so now M is a G manifold, so we can wonder about such a decomposition. So this is really motivated by Goodwilly's vision. So he has posed this question, and people have thought about it, and there were hints about what kind of properties you would want AG to satisfy in order for this to possibly fit into such a theorem. So maybe our project started more modestly. Okay, if you take a Waldhausen category with G action, can you build its equivariant K theory? Can we build it in such a way that this has the expected properties that were expected of AGM that I'm going to talk about in a second? And then, okay, if we can do that, can we actually relate it to equivariant h-cobordisms? And then eventually, can we prove the splitting? And then, of course, the next questions, but let's not get ahead of ourselves, would be can we actually relate this to equivariant diffeomorphisms? Okay, so for now, so let's see sort of what the expected properties were of Ag of M. Okay, so also what we would want here, of course, right, we don't want this to be some random thing. We want this to be defined as loops of some equivariant, so we'd want this to be somehow related to equivariant h-cobordism. So some spectrum which on the zero space level gives us equivariant h-cobordisms and then stabilized in some way. Okay, so that's the problem.
But on that board, you have some whitehead thing being the loops on an H-looking thing, and on the
sorry, yes,
board, yeah.
I messed this up.
And what kind of group is G?
Okay, so G, very good question. So G will be finite, not because of lack of interest in actions of orthogonal, orthogonal Lie group actions on manifolds, but just because the machinery that we're going to talk about for sure only works for G finite and not for compact Lie groups.
It's also not doctor's orders. It's not doctor's orders. Dog had it. It was doctor's orders. It's a joke, sorry.
So what was the doctor's order, Doc?
I'm allergic to compact Lie groups. My doctor told me to avoid them.
Oh, okay. Yes. So because Doug is allergic, we decided to not include compact Lie groups. It's not because we don't know how to do it. Okay, so on pi naught G, the thing to expect, so actually let me maybe move this to a different board. Okay, so there's a lot of work that had been done, and if, like Tom said, classical is anything before 2010, then this is very, 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 very classical. It's probably from the 70s and 80s. Well, let's start with the definition of an equivariant h-cobordism. So this is an equivariant h-cobordism if the inclusions are not just homotopy equivalences but G homotopy equivalences. So in particular, this means homotopy equivalences on all fixed points. So we can ask the same question as before. Given some W, is W, which is a G manifold and an equivariant h-cobordism, is it the trivial one? So now the trivial one means G diffeomorphic, and now note that the trivial one still has a G action coming from the G action on M. I still has trivial action. So I was going to write ... for the people to mention, but I also learned from Tom's talk that it's a bad idea. So maybe I'll just list verbally a bunch of people, and for some of them I will actually specify some results. But people who worked on this, on versions of the H and S cobordism theorems, were Illman, Rothenberg, Hauschild, Luke, Araki, Kawakubo, Browder, Quinn, and Steinberger, and more. But anyway, so many people have thought about this, so maybe let me mention, so Illman maybe was the first one to define an equivariant Whitehead group and equivariant Whitehead torsion as an element in here. Then let me mention a very good illustrative example of an h-cobordism theorem in this equivariant setting. Okay, so this is due to Araki and Kawakubo. Okay, so I don't have that on the board anymore, but remember, so non-equivariantly, right, we said that the torsion was 0 if and only if your h-coordinates most trivial. Now in the equivariant setting, so we have this equivariant torsion is 0 as an element of this equivariant Whitehead group if and only if. Okay, so now it's not going to be that it's trivial, but the statement is that there exists a representation V such that if you cross your h-cobordism with a representation disk, then it becomes trivial. I know, Mark, at some point you asked for an example. Well, if you had to do this, and I was going to give an example, but so there is an example in Luke's book, but it's way too complicated to give in the talk. However, the group is just Z mod 2. So there's an explicit example for a non-trivial h-coordinates with trivial Whitehead torsion. Okay, and then another theorem that I'll mention by Luke and Hauschild at least is that this equivariant Whitehead group splits over conjugacy classes into the, and now this is sort of crucial to what we're going to do and the indication of what we want to happen. So this is what happens on pi naught. This splits into the non-equivariant terms of fixed points and then homotopy orbits with respect to the Weyl groups. So we have seen these Weyl groups in several talks. Let me just remind you. So this is the normalizer of H mod H. Okay, and okay, so this is what we want to happen on pi naught. Okay, so now you can already imagine what one of the expected properties of AG of M was. So we wanted to have these kind of splittings over conjugacy classes of these Tom Dijk-like splittings. So we want a genuine G spectrum with these splittings on fixed points. So
WH sub G a space or a G space?
That's now just a space. So you take the fixed points, it doesn't have a G action anymore, but it has a WH action. And then we take homotopy orbits.
When did you take the fixed point?
X to the H.
But do you want G
On the
fixed
left
points
hand
on the
side.
left?
On the left hand side is WH sub G of X.
Oh, this one. That's X is a G space here.
But so it's
For conjugacy classes and subgroups.
Yes. Okay. So let's go back to this.
I mean, is the left
So let's see where I messed up. So here X is a G space.
and then WH sub G of X is,
Oh, this is this equivariant Whitehead group.
so it's a G space. So, but
Oh no, sorry, it's not a G space. Okay, it's a group.
oh,
This is the pi naught version. So far everything was groups.
Like basically fixed points.
Right. So we're still. I'm still talking about what we want to happen on pi naught. But you are very correctly predicting the abuse of notation that's about to happen. So so Dylan is right. Very soon this abuse of notation will happen when I will start calling WH like the space or spectrum. So far this is just this. Okay, so this is equivariant Whitehead group. Right, so remember in the s-cobordism theorem, right, we had diffeomorphous classes of h-cobordism were in correspondence to elements of this group. Now there's an equivariant version of this group. Right, so this is some element in this group. This is still a decomposition as groups. So these are the non-equivariant Whitehead groups. But it's good that we had this discussion because I will abuse notation and probably call Whitehead WG the spectrum that we want and the space that we want. Okay, so the theorem that we proved is that there exists a G spectrum AG of x. So again, x is a space with a g action with fixed points that have complete splittings, just like what we want to happen on pi naught. Okay, and similarly for h. Okay, so this is something that people had thought about, but the reason why this wasn't quite possible to construct this spectrum until now is that we really need this new technology of spectral Mackey functors as defined by Guillaume and Bowman-Osorno and Clark-Barwick. So we have also tried to build this as by delooping a single category, G category, and it turns out you can't quite do it like that. So I'm going to give the short proof idea. So I think some people have seen this construction before, but for those of you who have not seen it in my talks before, I'll go quickly over how we construct this. Okay, so if x has a g action, then we get a g action on this whole category Rx. So this is still the category of non-equivariant retractive spaces, right? Retractive space? Yes, I will tell you right now. Okay, great question. So I will tell you what the g action is, and in particular, I will tell you what this means. So an object in here is a space that has an inclusion and retraction map that compose to the identity. Okay, and then, right, so we get a g action just by decomposing and post-composing with a g action on x. And on morphisms, okay, so morphism between x and y, sorry, y and y prime is a map that makes such a diamond commute. And now, well, g dot this is going to be the same underlying map here, because if we, okay, so let's write this all out very explicitly. Okay, so y prime x. So here if I pre-compose, so if I do g inverse and then I and gr, okay, this is still going to commute. So very explicitly, this is what the action is. Okay, so if you have a Waldhausen category or a category with action, you can take its actual strict fixed points, or you can take the homotopy fixed points that I'll define in a second, and we can see pretty quickly that the fixed points are actually bad. So in this case, the fixed points are probably almost always empty, like the actual categorical fixed points. It would be a very strong condition to ask for this to be equal to I for all g. And more generally, right, so empty means it doesn't have a zero object in particular, so this is definitely not a Waldhausen category. And more generally, even if you had a g fixed zero object, there's still a coherence problem with the push outs, and in general these fixed points category are not Waldhausen, because the axiom with a push out fails. So instead we're going to take the homotopy fixed points, and I'll make a very concrete definition for these. So we'll just define these to be the actual fixed points of the category, the functor category, so all functors from EG to C, where this is a translation category. Okay, so then we have the following proposition that is going to be all the category theory that we need in order to make sense of everything that we need. So this and transfers. So there exists a two functor from G categories, pseudo-equivariant functors, and pseudo-equivariant natural transformations to G categories and equivariant functors and equivariant natural transformations, which on objects sends C to cat e.g. C. Okay, so a pseudo-equivariant functor is just, so if you think of a G category as a functor from BG to cat, that's just a pseudo-natural transformation as opposed to a natural transformation, which would be an equivariant functor. So, in other words, equivariance just holds up to coherent isomorphism. Okay, so if we do this, then we can actually strictify the pseudo-equivariant. So in particular, what this means is that if you have a pseudo-equivariant map, you won't get maps between the fixed points, but you will get maps between the homotopy fixed points. Okay, so some corollaries of this, and this is going to be all that we need using this proposition now. We can show that these categories are Waldhausen. So this problem goes away with the push-outs, and also we can show that we have transfer maps from the H1 homotopy fixed points to the H2 homotopy fixed points for all H1 included in H2.
But CX now means the C means RX? Or?
Yeah, so our C is going to be Rx in a second. So that's the category that we're interested in this talk.
You're saying that for any C, any G category C?
Yeah, for any G category C. So if you want to see, okay, I will give you the formula for the transfers. So it's really super easy. We're just using this proposition. So we saw lots of transfers in many talks. So I might as well see this so that you can see how easy it is. Well, once you know what you have to do. Okay, so proof. So let me maybe do the proof in the particular case. Let's go from some H to all of G. Right. So we want. So suppose we want a map between from H fixed points to G fixed points. So I'm not saying, we'll see in a second why you need a homotopy fixed points. Okay, so what is the H fixed points? This is just the G fixed points of the G mod H index product of C, right? So what we really want is a G map, so an equivariant map from this to this. Okay, so how would anyone define the transfer? Well, so of course you have G things here, you are going to send it. Okay, so we're assuming now that C has some kind of sum, right, to define the transfers. So in our case, it's going to be the wedge. Okay, so this is how you define the transfer. Okay, but this is not G equivariant, it's only pseudo-equivariant, because if you act first, you permute these and then you add them, and if you act after adding them, then they're added in that same order. So even if plus commutes with the G action strictly, this is still only going to be pseudo-equivariant. Right, so it's a matter of adding things in a different order. So we have those coherent isomorphisms. So this is only pseudo-equivariant. So we do not get, okay, so we're not going to get this, but we will get, so we can apply cat G to everything and then get an actual, after applying cat G, we can get an honest G map, and we get then the map on those fixed points, which are the homotopy fixed points. So of course these things have very, very explicit formulas. So we can write down very explicitly the formulas for these transfers. Okay, so now back to our example. Yeah, so this holds for any category with sum, but so now back to our example. The example that we care about is Rx. So we saw that the fixed points are bad, but the homotopy fixed points are what we'd want anyway. And the proposition is, so if we trace through what the homotopy fixed points are in this case, this is the category of H equivariant retractive spaces over X and H maps. Okay, so now we could make a G spectrum that has as its fixed points the K-theory of these categories, and we wouldn't have to use spectral Mackey functors for that. We could actually, this is a single category that we would also know how to apply S dot wants to and then use a delooping machine. So the Shimakawa or the Guillaume machine to actually write down an infinite loop G space. However, but this is not going to give us the spectrum that we want that has those splittings because, so right, this is a Waldhausen category, so what are the weak equivalences? The weak equivalences in here are coarse. So they are just the underlying weak equivalences that are H maps. Okay, so it turns out that this is actually an interesting G spectrum that we define to be, we're calling it AG coarse, and it turns out that these fixed points are Bruce Williams's bivariant A theory of a certain vibration. So that's not interesting, but it's not what we wanted for the geometric application to h-cobordisms. So what we have to do is just a small modification of this. So we're going to redefine. Okay, so now I'm going to, I'm sorry for the bad notation. I'm going to put the H on the inside. So these are not fixed points of any category right now. So I'm going to define this as having, so it's going to be the same objects and maps as this homotopy fixed point category. So H equivariant retractive spaces and H maps, but with the genuine weak equivalences. So weak equivalences on fixed points as opposed to just the coarse ones. Okay, so now the good news is we can still use our formulas for the transfer and restriction maps that we're getting over here, but well, we've changed the Waldhausen structure, so we need to check that transfers and restrictions are still exact.
Can I ask, what's acting now? You say on fixed points for what?
No, so I said this is not fixed points for anything.
No, but you say genuine weak equivalence.
H. So same objects and maps as this. So the objects are going to be H equivariant retractive spaces now, and H maps, and the weak equivalences are going to be the ones that are equivalences on subgroups of H, for all subgroups of H. Okay, so from this we will get a spectral Mackey functor. So of course you have to check a bunch of things, but this is the structure that builds into a spectral Mackey functor using, and a lot of hard work goes into this due to Guillaume, Bowman Osorno, Barwick. Okay, so using this framework, we can build our G spectrum now by assembling together these fixed points. Okay, so now the point is that with these categories, these are the ones that have the splittings. Right, so now we finally get what we wanted. So the K-theory so we're going to get a spectrum whose fixed points are going to be by definition the K-theories of these categories, and these were the ones that were known to have these splittings that we wanted. Right, and as you can see, it's not quite possible to achieve this by delooping a single category, because here, even though these just on objects and maps are the fixed points of a single category, which is caddy GRX, we change the weak equivalences in each one of the fixed point subcategories. So the only option seems to be to assemble these together in this way. Okay, so now how do we want to put all of this together? Okay, so now there's more work of more people that goes into this. So I'll start with the theorem.
Oh no, on that equivalence, I mean, on the right side you have h varying over.
Oh, yes, that's a mistake. So let me leave the h here and put the g here. And similarly for h's, and then you take subgroups of that. So Malkiewich and Dorabiala, so after talking to us, they got excited about this project too, and then they actually proved something very useful about our fixed points. So in particular, they also gave a proof of the splitting that's compatible. So they don't do anything with G spectra, but they prove that on fixed points, the suspension G spectrum, so this has a Tom Dijk splitting. So same kind of terms. This is why we're calling this a Tom Dijk-like splitting. That the inclusion, so on fixed points, the inclusion is compatible with the splittings. Okay, so of course this is very great news, because now so we have to sort of bump this up to a statement about G spectra. So now the idea is, right, we're going to define Hg of m as the fiber of the map from the suspension G spectrum into AGM. Okay, so we can do this, and then it will have the great property that we are after, that on fixed points it's infinite loop space. Well, or I will tell you now why we are after this. So now this is going to split into similar terms because of this compatibility. And now the question is, so what does this have to do? So we got terms into non-equivariant h-cobordism spaces or spectra. So what does this have to do with equivariant h-cobordism, right? So now we want to say that this is, well, so now this is a space, that this is a space of equivariant h-cobordisms stabilized somehow. So now this is the claim that we have learned from Goodwillie and Igusa, that there is, that you can make a definition of a space of equivariant h-cobordism, so stabilized. So maybe let me put a U here, which means, so now the stabilization is, you can probably already suspect this. You saw already earlier in even the pi-naught statement that we had to cross with a representation. So now this is now stabilized with representation disks. So it's the co-limit of h-coordinate spaces of M times dV over all representations. And so now these are spaces of equivariant h-cobordisms. Okay, so for the remaining time, let me just okay, so they actually claim something slightly weaker, but we're hoping to actually make it into this statement. So Goodwillie and Igusa are also working on this right now and proving good properties that we want of these equivariant h-cobordism spaces. Okay, so now in order to make sense of this and sort of the idea for the proof and what they've actually claimed, I have to introduce a few things. So I think I have 10 minutes. So let's switch gears a little and go very basic. So let's remember, okay, so we all know what an equivariant map is, or maybe we don't. Okay, so for an equivariant map, x to y, we have that the stabilizer Gx is included in the stabilizer of Gf. So now there's a definition of a slightly stronger notion. So we say that a map is isovariant. So an equivariant map is isovariant if we actually have equality for all x. So for those of you who are here for the first workshop, I want to advertise Sarah's project. She gave a talk about this notion. So I think it's a very not exploited notion by homotopy theorists, but it's a notion that definitely comes up in geometric topology when you think about, for example, h-cobordisms. So now what are the statements? So an isovariant h-cobordism, right, is such that these inclusions now are not just G homotopy equivalences, but isovariant G homotopy equivalences. Okay, so what does that mean? Okay, so know that in particular these are inclusions, and for inclusions this condition automatically holds. So those map are going to be isovariant no matter what. But isovariant G homotopy equivalence means that the backward map is isovariant, and the homotopies between the composites and the identities are also isovariant. So there's a lot more structure. And maybe a useful theorem by Hauschild is that, right, so for an equivariant map, we know it's an equivariant homotopy equivalence if and only if we have equivalences on the fixed points. So for an isovariant map, so, well, not a map in general, but for an h-cobordism, so something is an isovariant h-cobordism if and only if, so instead of fixed points, we have these other spaces that I will define in a second. So they're going to be complements of fixed points. So if these are weak homotopy equivalences, where x sub h, so these are the points in X that have isotropy exactly H. Okay, so maybe more useful. So what this means is we have the H fixed points, and you take away all the higher fixed points. So for all the bigger groups. Okay, so now going back to all the classical theorems. So the lies that I've been sweeping under the rug is that these statements usually hold for the isovariant and not the equivariant version, and for the equivariant versions only with extra hypotheses, and this is why we have to cross with representations to make these become the same. Okay, so now I can tell you more honest statements, like from the very, very, very classical past. Right, so for example, right, look, so we always will have some kind of conditions on our manifolds, or these manifolds that show up. So dimensions need to be of fixed points or these isotropy subspaces. Dimensions have to be bigger than 5, of course, for the classical h-cobordism theorems to apply. So, for example, right, there's an isovariant h-cobordism that just holds. So there's an isovariant Whitehead group and isovariant torsion defined in it, and that's actually 0 if and only if you are a trivial h-cobordism. So that actually holds exactly the way you would expect it. So this is an isovariant, so if this is an isovariant h-cobordism with isovariant torsion being 0, then this is if and only if this is trivial, with f restricted to M being the identity. Right, so this is the identity on M. And this isovariant Whitehead group classifies G diffeomorphism relative M. So up to isovariant h-cobordism. Then, so all the statements that you'd want usually hold for the isovariant case. So now what's the relationship between equivariant and isovariant? So with conditions, it turns out that the statements also hold for the equivariant case. So what are these conditions? So for the equivariant versions, so we need these what are called gap conditions on fixed points. Okay, so these are just conditions on the differences of dimensions of fixed points. And usually this gap condition is you want the difference of dimensions to be at least 3. So if you impose these conditions between dimensions of fixed points, it turns out, so important theorem is that if M satisfies these gap conditions, then an equivariant h-cobordism is an isovariant h-cobordism. Okay, and then the point is that if you cross with representations, well, of course, you can make these gap conditions become true because they are just differences of dimensions between the fixed points. Okay, so that's sort of the idea. And now, in the last minutes, let me maybe just give you the very rough idea of what Goodwill and Higusa have said and what we hope to show. Okay, so what Goodwill and Higusa have actually claimed is they have made this claim, but not for the space of equivariant h-cobordisms, but for the space of isovariant h-cobordisms. So we want to show the splitting, so it would probably be good if we can actually do the proof ourselves. So for the isovariant h-cobordisms, and then we want to show that, well, I should put a U here. So if we stabilize with respect to representations, that this is the same with just the equivariant ones. So hopefully I have made this believable with these old theorems that I have told you. So of course we'll have to do a bunch of work to actually make sense of it on the space level and spectrum level. Okay, so maybe I'll stop here. Dylan?
You said my name with a. I just wanted to know if the Siegel-Tom-Dieck splitting you have, like for suspension spectra, the pieces are also the geometric fixed points. Is that also true here? For the geometric fixed points of your A theory?
Yeah, I do not know that. That's a good question.
Wait, really? You can't identify the transfers?
What's that?
I mean, you're saying you can't identify the transfers?
Yes. The transfers for sure. We can write down very explicit formulas for them.
Then you can express the geometric fixed points in terms of that. If it's just the inclusion, for
Like
example,
if
for
it's
the-
doing
Yeah, so we can probably check this. Like we just haven't thought about it, but it sounds like even after this talk we can probably check this.